So now we will talk about cryptographic keys, how you establish them, how you manage them, what happens, and all that kind of stuff. So يعني في مجموعة من الترمينولوجيز that we would use اللي هي like entity authentication, for example. Entity authentication, and sometimes you want to use cryptography to basically know that you're talking to a specific entity right now in its life. It's not a message that it sent like a couple of hours ago. It's a message that it's sent right now in its life. And sometimes you want to do this both ways. Each one want to kind of like make sure the other one is live and now. This is why we do mutual entity authentication. In key agreements, sometimes what we want is the two parties, the sender and the receiver, مثلا, they both together agree on a key. And then that key becomes common. And sometimes that one party, like let's say مثلا, it's a client and a server, مثلا, a client creates the key or the server creates the key and then sends the key to the other person. So we have a trusted entity that actually creates the key and shares the key with the other parties. So this is what we call a key distribution protocol. The key, the management of the keys is absolutely required in symmetric algorithm, that the key will always be secret. لأنه the encryption key and the decryption key are the same, so always the key should be secret. In asymmetric algorithm or public key algorithms, we need to do two things. We need to keep the private key secret, but also we need to keep the public key authentic. بمعنى, if the public key comes out to come and say, you know, this key belongs مثلا to Mohammed, we need to have an authentic way that we know for sure it belongs to Mohammed, and no one is claiming that this key belongs to Mohammed, because some people can come to the network and say, oh, like this is Mohammed's key, and مثلا everyone goes and encrypt messages and send it thinking they're sending the messages to Mohammed. So we need to keep the private key private, but also we need to keep the public key authentic. And in those things, in key management, this is where design and architecture comes to play. There are some standards in different parts, but how to manage a key in the system, this is where you as a security professional, you need to be able to look at the different components and decide how to design this. طبعا, this is the life cycle of a key. You generate the keys. Let me just do some annotation. So you basically generate the keys. You establish them, or using key agreement or key distribution. You store them and save them in memory or storage. Sometimes you put them in a backup, and then when you want to use them, you use them. Sometimes you archive them if you don't want to use them anymore, but want to keep them archived. And then when you're done with them, you want to absolutely delete them and destroy them, not just simply delete them. And sometimes while using the keys, you want to change the keys after a while, and this is where you go to key change and then all the way back again to key generation. So in each one of those, there is actually a standard and a way and to do it in a secure way. And every time you design a system, you need to make sure that each one of those steps, the key is at the same level of safety. لأنه if you do the super secure, but you back them insecurely, خلاص, all what the attacker should do, come here, steal the key, and then break your whole algorithm. So if any of those fails or do less security than the others, it becomes the weakest point and the attack points in the system. So one of the most common key agreement where two parties agree on a key is something called Diffie-Hellman key agreement algorithm. And it was designed in 1976. Two guys, Martin Hellman and Whitfield Diffie, created this where, in a protocol, two parties, they don't know each other. they exchange a couple of messages, then those two parties have a secret, and anyone reading the messages that are exchanged, they cannot know the secret. So a client and a server talking to each other the first time, they can send like 3 messages, then suddenly just those 2 people have a secret that if anyone just looking at the messages, just silently looking, they cannot figure out the secret, which is a very, very beautiful algorithm that we will talk about in a second. So this is the algorithm. It's very simple. So Alice and Bob want to create a common secret. They don't know each other. They never met each other before. But they know the network is insecure. There may be anyone who's listening in this network. Right? So what Alice does, طبعا they agree on 2 things. G and P are public. Right? They decide on G and P, and everyone knows. Everyone knows G, everyone knows P. So what Alice does, she chooses A, and then she computes G to the A modulo P. And we know from discrete logarithm, if you have this, to reverse it and figure A, it takes exponential time. Even if you know G and P, it takes exponential time or brute force. So this takes a lot of time to reverse, and exponential, which means needs, hundreds if not thousands of years to do it. And then Alice sends this to Bob. Bob, at the same time, chooses B at random and computes G to the B mod P and send it to Alice. Right? So Alice has this. Just a second. So Alice receives this. Hello. And then she also has A. So she takes this, raise it to the power of A. So it becomes G to the A B mod P. Right? So if you raise anything here, like all of this just simply come here. And we also know that Bob receives this, and he raises it to the power B because this is the B that he has, and only Bob knows B. Even Alice doesn't know B. And only Alice knows A, even Bob don't know A. But if you raise this to this, you actually know it's actually equal to G to the A B mod P. And this becomes the common secret between the two. But if someone has this, everyone sees this and everyone sees this. If you multiply those 2 numbers together, it gives you G to the A plus B. And then when you multiply two numbers with exponents, it actually becomes an addition of the exponents. The only way to get G to the A B mod P is either you know A and take this one and raise it to the power A, and only Alice knows A, or you know B and take this one and raise it to the power B, and only B knows B, or know A and B together, which no one basically knows, or take this and reverse B out, and we know from discrete logarithm this is exponential time, or take this and reverse A back, and we know from discrete logarithm this takes exponential time. Very simple algorithm, very beautiful, and 2 people, they don't know each other, they can just send a message in the air, even if they use broadcast, and then suddenly they have a common secret that no one listening to this can actually know or figure out the secret. طيب, what if تفضل محمد. تفضل.
إذا أليس ما تعرف B وبوب ما يعرف A كيف يحسبونها في الأخير؟
So Alice takes this. Alice knows G to the A, G to the B mod P, صح? Everyone knows this, right? So she takes this and raises it to the power A. So if you take this and raise it, Alice knows A, she raises it to the power A. So if you raise it to the power A, then it becomes G to the AB mod P. Until like when you have two exponents, you raise one and then you raise it to the other one, mathematics. Then it's the multiplication of A and B. It becomes G to the A multiplied by B, صح? And also Bob knows B, and Bob receives this. He takes this, raises it to the power B. And then we know, like you take this and then you do multiplication. And the order in multiplication doesn't matter. G to the B times A or G to the A times B. And it becomes G to the AB mod P. So Bob gets this and Alice gets this. Okay. So, well, we said this is secure if someone is just listening. What if someone is not listening, but actually intercepting in the message and starting to manipulate messages? And this is like this example. So we actually have Charlie, right? So trying to get between Alice and Bob. Hello? So what Charlie says, okay, like I'm able to be in the middle and start to manipulate things. Hello? So then what happens is Charlie gets to G to the A mod P or N, whatever that is, and then basically take it and stop it. Hello? And then sends to Bob, instead of G to the A, he sends to Bob G to the C mod P or mod N, right? And then Bob sends G to the B mod N. Charlie stops it and sends G to the C mod N. So Charlie creates this message and sends it once to Bob and once to Alice. So Charlie only knows C and he knows everything message is sent here. Alice knows A and Bob knows B. So if we take those messages, so A receives this, she raises it to the power A, and then she has G to the A C mod N. But C is actually sent by Charlie. Charlie, he's not just listening. Charlie is actually stopping the messages and sending his own messages. And here, like Bob actually receives this, raises it to the power B. He gets G to the C B mod N. So then Alice thinks she has a key with Bob. She encrypts things using this key. It gets here. Charlie also has this key, and he gets this. He raises it to the C, and he gets exactly the same key. So he can decrypt the message, and then encrypt the message again using this key, and he can get this key because he receives this. He just raises it to C. And then Bob the same. So he sits in the middle, encrypt, decrypt, encrypt, decrypt, decrypt, encrypt, decrypt, encrypt, and be able to intercept everything in the middle. And there is a way to protect against this in an algorithm called station-to-station protocol, and this is called man-in-the-middle attack. So Charlie is a man in the middle sitting there and stopping messages back and forth and doing manipulation. And because he was at the beginning of the algorithm, he is able to inject himself correctly as man in the middle in the whole algorithm. So this is Diffie-Hellman key exchange protocol, or key agreement protocol, which is a great protocol. The biggest challenge with this if we do this معناها for n parties, n keys, عفوا for n parties أنا يعني مثلا Alice wants to talk to Bob, she has a key. And then if we have Charlie and we have Mallory, then we realize Alice needs a key with Bob, Alice needs a key with Charlie, Alice needs a key with Mallory, Alice needs a key with David. So, and then Bob needs a key with Charlie, Bob needs a key with Mallory, Bob needs a key with Alice, Bob needs a key with David. So then we start to have lots and lots and lots of keys. And the total number of keys in this case is actually, we need for the n players, for each one of those, for each one of those, يعني for Alice, right? Alice needs n minus 1 keys, صح? So for each one of those, Alice needs n minus 1 keys. She needs like, يعني in this case 5. عفوا, yeah, n is 5, which is the total number of parties. So Alice needs 4 keys. But also B needs 4 keys, and C needs 4 keys, and Mallory needs 4 keys, and David needs 4 keys. So for each one of those, for each n, we need n minus 1 keys. One final piece, actually, the key between Alice and Bob is the same. Right? So every party, so we counted this twice, and then we counted this twice, and then we counted this twice. So to do this, we divide by 2. So the total number of keys in this system is n times n minus 1 divided by 2, which is roughly is n squared. It's not exactly, it's actually less than n squared. But it is roughly as an approximation of n squared. So إذا عندك أنت 1,000 users, you need 1,000,000 key in the system, roughly, which is a huge number of keys, and it's not practical. Right? So then we need something called a key distribution protocol. بمعنى we have a trusted third party, and then that trusted third party, يعني انت تخيل انت عندك like server، تخيل في الجامعة، right? You have a server, and then you have, let's say 10,000 students, and then maybe you have a 1,000 servers. So you need lots of keys. Ideally, you want the student to have 1 key to communicate with everything they need, including communicating with another student. So how to do this? We use a key distribution algorithm using a trusted third party. There is a third party that everyone trusts that basically can help you in that process, and we will see a practical example. So this is one of the oldest algorithms called Needham and Schroeder protocol. So Needham and Schroeder protocol, يقول لك they introduce a trusted third party called T. And then you have, let's say, user A and user B. And every user has a key with the trusted third party. So A has a key with T, B has a key with T, C has a key with T, M has a key with T, with D, and that's it. Only 1 key with T. And this key is called like KAT between A and T, KBT between B and T, and whatever. So what we want is like the ability, now let's say A wants to communicate to B, but A has no key with B. So if A has no key with B, she needs to talk to T. So when A goes to T and say, hey, I'm A, I want to communicate to B, and here is a nonce. So N, لما نقول NA, so N is a nonce. So a nonce is actually, N stands for number used once, and this is why we say it's N for nonce, used once We combine those two, it becomes a nonce. So this is number used once and generated by A, and it's a random number. Okay, so what happens in no, like A sends the following message: I'm A, I want to talk to B, and this is my nonce. So, and sends it to T. So what T does, you go like, okay, if you're A, here is an encryption using the key that only known between A and T. And what I'm going to put into this the following. I'm going to put your nonce, A, the one that you just sent, and I'm going to put the identity of B. You said you want to talk to B. Here is like a key B. And I'm going to put key K. Also, in the same message, I'm going to put an encryption using a key between B and T that A don't know, and it has key K and message A. And I will close this, and I'll close the bigger message. Okay, so this message here has the nonce, has B, the address of B, for example. Maybe if it's an email address, it's the address, so it's the identity of B, and the key K, and this message. This is encrypted. K and A is encrypted using a key between B and T. Alice cannot open this message because she doesn't have the key BT key. But Alice can come and receive this message, and then she opens it. First thing that she checks is the nonce here the same nonce that I just sent. And the reason is because I want to make sure that T is replying to me right now, because I just sent the nonce. So if we don't have this, an attacker here called Mallory can sit in the system, and like yesterday, Alice asked to connect with B, and then because there is no nonce, T sends this message without the nonce, BK, EBT, whatever, right? And Mallory is sitting, and then Mallory saves this message. It's encrypted, she can't open it, but she saves it. And then she waits. But then when Alice communicates to T, Mallory can jump and stop the message from T and send this old message from yesterday, fooling Alex. But what we're doing here is actually saying, no, if you send me a message from yesterday, it will have a different nonce. Right? So it doesn't matter if you're here and listening, you can't send me this message again. Hello? So Alice opens this message, she checks this, perfect, she checks this, amazing. أنا بتأكد إنه maybe someone in the middle changes B to C. No, I want to make sure what T understood that I want to talk to B. For now I know that this key, is exactly the same key inside here, even though if I can't open this. Why? لأنه fundamentally fundamentally here what is happening is I know that this is a key that I just asked from T that has for my answer to communicate with B, and it has the following structure. So now I know this key will be used between me and B. So Alice goes, okay, perfect. I got this message. So I open this, I go to B, and I send to B this message. And I tell B, okay, I want to communicate with you, B. Here is the secret that is coming from T. So B take this, opens this message, creates NB, which is a number used once, a nonce, and encrypts it using the key. Alice comes, opens this message because she has K received here, take the number inside, -1, and send it back to Bob. So now we know that there is a secret between A and B, which is K. They can talk, communicate with it. A and only A needed one key with T, and T was able to create trust between A and B. Right? There is another more common algorithm used actually in Windows called Kerberos. It uses the idea of Needham-Schroeder and develops it and creates multiple keys in multiple sessions. لأنه the main issue with Kerberos is actually I need a key from, يعني anytime that I want to talk to B, C, a server, whatever, I need to go and talk to T. So it needs a key every time I want to talk to a service. So what Kerberos does is يقول لك خلاص, just like when you sign once a day and then you have a session, it actually implements this in a really, really great way, which is a way to basically have one session key and then can repeat using this key throughout the session. So the way that Kerberos does this is أول شيء عندك the authentication server. So basically you do it once per session. Okay? So the way that you do this is you say, hey, I want to log in with my password to get into the system. You get one session key. And every time you want to talk to a new application, another user, a file server, you actually go here with that session key once and get a key to talk to the server and then use that server. You want to talk to another server, you repeat 2 and 3. Every time you want to talk to a new service or another user, you actually repeat 2 and 3, but you only do one once per session. And this is what we say here, like the daily key, which is the key A here, is the session key. And every time you want to talk to an application server, you basically create an application key K and use it. The problem with Kerberos, there is a single point of failure. So if anyone kills the server, then no other user can talk to any other user in the system. And it can work inside an organization. يعني مثلا في الجامعة, you can have a server that actually creates a session key, whatever, yada, 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 all that kind of stuff. And then, but it doesn't scale to the whole internet, because if someone wants to break the internet, they can just simply kill and break that server. Okay. So the final piece around keys, احنا لما تذكروا تكلمنا عن public key algorithms, we said there's two things. You want to keep the key secret, but also you want to ensure authenticity of the public key. So this is why we use the notion of what is called certificate authorities. And certificate authority is like a trusted third party that has one purpose, to say in the public key هذا belongs to this user. And then it actually puts a certificate that has a stamp on it, not a physical, like a digital certificate, and we'll talk about how it works. And we'll say like, this is the owner, maybe this is his email and his name and his address. This is the algorithm that this public key is using. Maybe it's RSA, El Gamal, it's 1024 bits, it's 2048 bits, and whatever, and then puts the public key in it and says like, this key is valid from day one, this date, kada, 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 and all that kind of stuff. And then signs this document using the certificate authority private key. Okay? And then the public key of the certificate authority is known. Now, if you go to your computer, in any computer, there is like 200 certificate authorities that has the public keys pre-installed in the operating system, which means it is trusted by everyone. So if anyone comes and brings a certificate, you know for a fact that this is coming from this very specific certificate authority. Let's take an example. Right? I'll just stop sharing the screen, and I will share another screen. So let's take the example of, Google.com. So in Google, you go to Google, you notice that this is like this lock tells you Safari using encrypted connection to Google.com, show the certificate. So we show the certificate. We see here, there are like global signing a certificate called GTSCA 101, signing a certificate for Google. طيب. So we see this Google.com issued by and signed by a certificate authority called GTSCA 101. And this certificate expired Thursday, November 26 at 2020 at 9:42 minutes 46 seconds AM Arabian Standard Time. And the operating system checked this certificate and said it's valid. So let's see, what does it say? It says, this is Google.com actually exists in the US, California as the state, Mountain View. The organization name is Google LLC. This is the common name, the URL, right? Who's the issuer? The issuer is something called GTS, Google Trust Service. And this is the serial number for the certificate. And this is a certificate, like the document is a version 3. This is the standard. And this is a certificate using RSA encryption with SHA-256. Right? Because RSA always uses hashing with it. So telling me what hashing algorithm is, احنا شفنا SHA-256 in class, and we saw RSA in class. When did it start? It started September 3rd, 2020, and it will expire November 26, 2020. What is the public key? It's an elliptic curve public key algorithm. The parameter is the following. This is exactly the public key, written in hexadecimal in 65 different bytes. Right? So this is the key size, 256. What do I use this key for? I use it to encrypt, to verify, and to derive data. Derive هنا بمعنى deriving other keys. And what is the signature? احنا قلنا like this GTS signs Google, and then if I sign something, I need to include the signature. This is the signature. It's a 256 different bytes. Right? And there are like more and more details here that we'll get to some in a minute. Like, this is signed by who? Signed by Google.com. Signed by GTSCA 101 to Google.com. Like, GTSCA 101, أنا ما أعرفها. It's not actually in my computer. But then GTS is actually in the US, yada, yada, yada. It started from December, it expires December 15, 2021. And what is it used? Let's go back. It is used to encrypt and verify and derive. Right? طبعا, who signed this? We look something called Global Sign Root CA. These are the root CA. There is about 200 of them that come pre-installed in your computer. If you come here, you say, you can see this is already their public key. It is already installed in your computer. It's already trusted. It is installed in the computer, and it comes, and Global Sign has an agreement with all the computer operating systems, with Microsoft, with Apple, and it comes pre-installed in the operating system that this is trusted. This is the public key of Global Sign. And تلاحظون هنا, like Global Sign, let's see who issued this. Look, this is Global Sign Root CAR2 and issued by Global Sign Root CAR2. So it issues a certificate for itself, and it actually signs it using this public key, and then it stores in the system. and هنا نلاحظ this is issued by Global Sign and signed by Global Sign, but it's for Google Trust Services. And then Google هنا, it's actually issued by Google Trust Services, and it is for Google itself, right? So this is basically how I know this is the public key for Google. So if I want to encrypt it, my connection with Google is encrypted. So how do I send it encrypted? I actually download the certificate, get Google public key, where is it? Public key, and ensure that every message between me and Google is encrypted. This is why we have the lock and everything is encrypted, right? So this is fundamentally how this works. And now I know this key, Google gives me this, and I know this key is actually fundamentally for Google. إبراهيم تفضل.
كيف اطلع مثل المعلومات هذه اذا كان النظام حقي ويندوز؟
Exactly the same thing. It could depend what browser you have, and you just use it. Let's take an example right now. Let's say we use the Chrome browser, مثلا.
Okay.
Let's take the same exact example on Chrome. Okay, so if I share my screen and I go here and I go here, I can exactly look. The connection is secure. This is a certificate, and I open this. Exactly the same information that we had, right? So this. Right. So this is how we. تفضل.
هي نفسها شهادة ال SSL ولا شيء ثاني؟
Yes, this is the SSL certificate. بالضبط.
تمام.
So this is what we just talked about, and the root CA that has intermediate CAs, and then you have the clients and all that kind of stuff. And this is what we just said, the information, certificate, core, public key, extensions, whatever. The final concept that we want to talk about, and sometimes until you issue certificate, but let's say Google, or let's say I had my private key, right? So in my website, I had my certificate, and then I had my own private key. And then what happened I lost my private key, right? So let's say that I actually lost my private key. And if I did lose my private key, it means, I need to go and tell, let's take the following example. Right? So let's say in my website, right? So you go here, certificate, let's encrypt, have given me a certificate, and then there is my public key, right? لاحظوا انه 512 bytes. It's actually a large public key لاني I'm a security person and I wanted a really large public key, right? And I got this large public key. But we always know there's a private key for the server to decrypt stuff. Let's say I actually lost my private key. And then I want to tell the world, the key, this particular key that comes with this serial number that is issued by an organization called Let's Encrypt to me, to my website, I want it to be revoked. I want every time someone uses this, they know it's revoked. And this is where basically we tell in every certificate, when you get this certificate, go and check if this certificate has been revoked or not. And there are two ways to check if the certificate had been revoked. Way number one, let me just try to find this. Where is this? Okay, so the first way is actually something called a OCSP, Online Certificate Status Protocol. So I send a ping to the server and I tell them this certificate with this serial number, is it valid or not? And then the server tells me yes, this is valid, or it tells me no, this is not valid. The other way, which is the older way to do it, and let's do it with, I think Google certificate has this. Let's just see. If we go down. Okay, CRL distribution points. So every time I download the CRL, right? If I even click on it, say, hey, do you want to download this file? I'll say no. Oh, okay, let's see where I am. Yeah, so I actually can download this file if I click on it. So if I copy, every time it takes me to Safari. Anyhow, so if I can take this and actually download the CRL, my operating system, and check. CRL is actually a list that tells you the certificates that have been revocated by GTS CA 101. And they update this list periodically. Every time they actually put and add the revocated certificate. So if my computer detects this certificate has been revocated, then it means this is not a valid certificate and I should not use it because it was revocated. And this is exactly what we say here. There is two-way, like either expiry, if the certificate expires, khalas. But if it's not expired and I want to revocate it and I want to tell the world this is not a valid certificate anymore, please don't use it, I can revocate it and tell the world it is revocated using one of those two algorithms. So this is basically all what we will be covering around cryptography and keys. And then from the following lectures, we'll start to go into like software security and other components.